Welcome back, everybody, to another Algebra 1 lesson. Today we are on Big Ideas, section 7.6. Now, the interesting thing about 7.6 is there are not a lot of notes provided. They don't give you a lot of instructions in the Big Ideas student journal or anything like that. And that's because, for one of the things that we're talking about today, we already kind of know how to do it. After that, we are going to be learning two different methods that you'll be able to pick and choose which you want to use to solve sort of the leftover problems, is what I'll call them. Before we get started, I want to remind you all what a greatest common factor is. We've talked about this in the past before in previous sections, but the greatest common factor is something that you can pull out from all of your terms. So for instance, if I gave you this, and I asked you to factor out the greatest common factor, we know about this. We know about the process of factoring. We would just pull out whatever is in common between these two and put the rest in parentheses. When I say pull out a number, I mean that we are dividing by that number. So we ask ourselves, what can 2x squared and 6 both be divided by? Well, 2 and 6 can both be divided by 2. So we put a 2 out front. Whatever's left over after we divide both our terms by 2 is what we put in parentheses. So when we divide 2x squared by 2, it's the same as just taking out the 2. We're left with x squared. And 6 divided by 2, well, that's just 3. So this would be how we take out the greatest common factor. However, there are some problems that we'll see that don't involve just taking it out of two terms, but from many terms. If we flip to page 232, you will see some such problems. The top 6 problems of this extra practice, so all these up here, actually have a greatest common factor. And here is a rule that we must follow. If you can factor something out, you must factor something out. It seems really weird, but there are some problems that are just unsolvable unless you can factor something out at the start. A perfect example of this would be problem number 5. If we took a look at problem number 5 and we tried some of our previous methods, we might ask ourselves what multiplies to make 50 and what adds to make 55. There's no two numbers that multiply to make 50 and add to make 55. That's absurd. So we have to instead factor out the greatest common factor. And what can all 3 of these terms be divided by? Well, they can all be divided by 5. 5s squared has a 5 in it. 55s, well, that's just divisible by 5. 55 can be divided by 5. And 50 can be divided by 5. So we would pull out the 5 and put whatever's left over in parentheses. We would have s squared, since 5s squared divided by 5 is just s squared. 55s divided by 5, well, we would just divide 55 by 5. That's 11. So we get plus 11s. And 50 divided by 5, well, that's just 10. We might be tempted to stop here. We might be tempted to say, oh, we factor out the 5, we are good. But last section, 7.5, didn't we learn how to factor something like this middle part? Anytime you have something that can still be factored, you must keep going. This is what it means to factor something completely. But what happens to this 5? Well, the good news is the 5 is just going to stick around. We've factored out the 5, so we've already simplified this problem in some way. We don't want to put the 5 back into the parentheses. We want to leave it outside. We went through all that effort in the first place. Why put it back in? But we do know that our answer is going to be 5 times a binomial and a binomial, since a trinomial can be factored as a binomial and a binomial. In order to factor something like this, we will use the simple factoring method that we learned in 7.5. In 7.5, we learned that the last term is going to go on top, so our last term is 10. Our middle term is going to go on bottom, that's 11. So what multiplies to make 10 and adds to make 11? Well, 10 times 1 is 10, and 10 plus 1 is 11. When we write our answer, think about what these first two terms have to be in order to make s squared. The only way to make s squared is s times s. So our first terms are always just the variable that's being squared, at least in simple factoring. And then we put our answers in afterwards. This is s plus 10 and s plus 1. And we're done. This method has a name. We are going to call this factoring by GCF, by greatest common factor. If you can pull something out from all terms, you must pull something out from all terms. But let's take a look at some of the problems below this little median here. In fact, let's try and take a look at problem number 8, for instance. What's the issue here? Why can't we factor this by the greatest common factor for problem number 8? Well, we might try a couple of things. We might say, okay, so 6 and 4 can both be divided by 2, so can't we pull out a 2? But negative 11 can't be divided by 2, so that's out. You might say, oh, this term has a k, this term has a k. Oh, but this last term doesn't have a k, so we can't pull a k out either. Huh. We can't factor anything out of problem number 8, can we? Well, the good news is there are still methods to work with this problem. We're going to learn 2 of these methods today. Before we learn these methods, I want to give a little bit more of an idea what the structure of trinomials looks like. So every trinomial that we've seen so far, all of these, follows sort of a similar format. You see how it's 3 terms being added or subtracted. You have a squared term, a term with 1 variable, and a term with no variables. This is known as the standard form of a polynomial. You're always going to have an x squared term, or s squared, or p squared, or whatever you might have, plus an x term, and then plus some unit, some whole number. Well, we've called our whole number, the last number, c before. C is some constant. That's what C stands for. It could just be any number. Our middle number, let's call b, the number that's multiplying our variable. We learned how to factor something that looks like this last time. It's just like this s squared plus 11s plus 10. The difference is, oops, these problems down here have another number in front of our squared term, like 12, or 6, or 9. We're going to call this number our a value. So, a polynomial can be written in the form ax squared plus bx plus c. When you factor by a GCF, you do this when you have an a term that can be factored out. When your a term can be factored out. When it cannot be factored out, we have 2 new methods we're going to learn. The AC method and the box method. And again, this happens when your a term cannot be factored out. Let me give you an example of a problem where our a term cannot be factored out. Let's say we had the problem 3x squared plus 11x plus 6. Why can't our a term be factored out? Think about it. Why can't we just factor by a greatest common factor and call it a day? Our first number can be divided by 3. Our last number can be divided by 3. But our middle number, 11, cannot be divided by 3 evenly. So we cannot factor out a 3. The AC method and the box method are methods that you would use anytime you have an a term that cannot be factored out. what I'm going to do is this. I'm going to write out this term here. And we're going to start doing a process of problem solving to figure out what we can do from here. Now, I do want to mention something very important. The AC method and the box method are not the end-all be-all methods for factoring when you have an A term. In fact, there are approximately 16 different officially recognized ways of factoring out when you have an A term, or factoring this trinomial when you have an A term. 16. I am not about to teach you 16 methods. No, that's a lot. You can learn a couple extra methods if you feel like these methods aren't working for you. There are methods called the California method and the slip and slide method. There's methods from all over the world for doing stuff like this. However, the two that I've picked are the AC method and the box method because they each have some benefit to it. The AC method's benefit is going to be that there is a built-in check near the end of the problem that makes sure you did it correctly. If you do the AC method 100% fine and you get to this check, you know that the rest of the problem will be 100% correct. It's very useful on a test. The box method is nice because it's easier and it's a lot more organized. But again, they both start out the same way. If we think about this problem, there are no two numbers that will multiply to make 6 and add to make 11. So if we were to set up a combinator here to try and figure it out, it'd be very difficult. It'd be very difficult. Both the AC method and the box method get around this by doing a little bit of a cheat. Yes, a little bit of a cheat method. Since there's no way of doing this, we are going to borrow our A value and put it with our C value in order to make something that can be put into a combinator. Later down the line, we'll have to correct this cheat by taking back out what we put in. But we're cheating by taking this 3, and we're going to combine it with 6 by multiplication. In other words, we are taking our A value and multiplying it with our C value. That's where the AC comes from in AC method. We're going to put A times C on top of our combinator instead of just C. Again, with the AC method and the box method, you're going to start by taking your A times your C and putting it on top. So 3 times 6 is 18. On the bottom, we just have our B value like normal, our middle number. That's 11. So the first step is to set up a combinator wherein we have our A times C on top. That's our cheat. What multiplies to make 18 and adds to make 11? Well, as we think about this, we know that 9 and 2 can multiply to make 18 and add to make 11. So we have solved our combinator here. But would it make sense to have x plus 9 and x plus 2 as our two answers? No, because 9 times 2 at the end would not give us 6, it would give us this 18 we created. So we can't just write out our answer as x plus 9, x plus 2 like we would with the simple factoring method, like the one we did here. Instead, we are going to go all the way back to lesson 7.5 and remember how we first learned factoring. If we recall, we know that 3x squared is our first two terms multiplied. Our 6 is our last two terms of our answer multiplied. This 11 is our outer and inner terms added together. If we knew what the outer and inner terms were, we might be able to break up the problem a little bit more and figure it out. Do we know what the outer and inner terms must be that combine to make 11? If you said 9x and 2x, you're correct. By solving a combinator, we know what this 11x started off as. We know where the 11x came from. We know that it started off with the extended polynomial, 3x squared, and 11x is made up of 9x plus 2x. So plus 9x plus 2x plus 6. Very nice. that is going to be step 2. Step 2 is splitting up your trinomial into a quadrant, or into something that has 4 terms, with these middle 2 splitting the 11x. Now, this problem looks a little bit more complicated. And there are 2 methods for what we can do next. This is where the box method and the AC method split. So I'm going to split my paper down the middle so that we can work on the AC method here on the left and the box method on the right. Again, you always want to set it up this way, where you have these 4 terms, because this is going to be the best way of working through it now. The AC method goes like this. Once you have your 4 terms all laid out, 4 terms is a lot to deal with, right? That's a lot to sort of manage. So we're going to break this problem up into smaller bits through a process called grouping. We are going to group together our first 2 terms in parentheses and our last 2 terms in parentheses. The reason we did this is, now, if this was just our problem, we know how to factor something like this. Notice what we can do with this. There's a greatest common factor. And we know to factor by GCF, we just pull out the greatest common factor and put it in front. So, just looking at these first 2, what's the greatest common factor? What's the biggest thing we can pull out from both 3x squared and 9x? Well, both can be divided by 3. That's a good start. Is there anything else they have in common? They both have an x. This one has 2 of them, actually, and this one has 1 of them. So let's pull out 3x and see what's left over in the parentheses. When we pull out 3x from 3x squared, well, we're just left with 1x. So we're going to write it as x in here. And 9x divided by 3x is the same as 9 divided by 3 and x divided by x. 9 divided by 3 is 3, and x divided by itself is just 1. So our answer is just 3 times 1. Our inner parentheses is x plus 3, because 9x divided by 3x is 3, 3x squared divided by 3x is x. Let's do the same thing with the second pair, because if you do the AC method, you should always be able to pull out something, even if it's just the number 1. Even if the smallest thing that can divide both of them is just the positive 1, you can pull it out. So let's pull out something from 2x and 6. Well, we did a problem similar to this before, and we know that 2x and 6 are both divisible by 2. So we take these, and we put a plus 2, because it's positive. And what's left over, we divide both these by 2. 2x divided by 2 is x. 6 divided by 2 is 3. So the third step was grouping them. The fourth step was factoring your individual groups. And we might notice something strange that happens after you factor out. What's interesting or notable about this, about our answer here? Notice that our parentheses are the exact same. This is super important. This is what I meant when I said there is a built-in check. If you are doing the AC method, you can guarantee that you're doing it correctly if your parentheses match. If they match, you did it correctly. You pulled out the right common factors. If they don't, it just means that there's still something to pull out from one of your terms. You might have missed something or not pulled out enough. If the terms match, you are correct. Now, this is where things are going to get a little bit funky. This is the last step. But let me explain something to you all real quick, something that we already kind of know. Let's say we had something like this. Let's say we had 3x times y plus 2 times y. We know from factoring by the greatest common factor that if there's something in common, we can pull it out. What's in common between these two? Both of these have a y in parentheses, so we would pull out our y in parentheses from both terms, and the rest we would put into parentheses, 3x plus 2. It turns out it's the same even if what's inside of parentheses is a little more complicated. Up here, we have x plus 3 on both our two terms. It's a little more complicated, but that means we can pull out x plus 3 from both terms. Let's pull out an x plus 3 from both and put it in front like we always have been. So we take our x plus 3's and we put them in parentheses in front because we pull it out from both terms. And with whatever's left over, we put into parentheses, right? We have a 3x left over, we have a plus 2 left over. So we now have two binomials. It turns out this is our answer. It's super weird how it works. But by factoring over and over and over again using our AC method, by grouping here in the middle and pulling out again and again, we actually factored our trinomial. That's the fifth step, is to pull out the x plus 3's and put whatever's left over in parentheses. That's the AC method. This method is tough. It's tough because it is a very strange method and the steps are a little bit more complex. But it's very valuable because it has this check here. As long as what's in the parentheses is the same, you know you're doing it right, and it means that you're going to get the right answer. Let's take a look at a little bit of an easier method, though, the box method. 3x squared plus 9x plus 2x plus 6. The box method goes like this. The first thing we're going to do is create, you guessed it, a box. Yeah, I know, big shocker there. But you're going to create a box that has 4 little boxes inside of it. Inside of these 4 boxes, you are going to put all of your terms. However, there is a restriction. The first term must go in the first box. So 3x squared is going to go here. And the last term, this plus 6, is going to go in the last box. So we put a 6 here. The other 2 terms, doesn't really matter where you put them. You can swap them around all you want. So I'm going to put my 9x here and my 2x here. But I could have flipped them as well. Why not? That's the step here. You want to put everything into the boxes. After you've put everything into the boxes, now begins the process of factoring. This method is a lot more organized, and all it asks of you is to factor out every row and every column. What does that mean? Let's take a look at this first row. What's in common between these two? And if you paid attention to the last problem, you might know. Well, 3x squared and 9x, you can take out a 3 from both of them, and you can take out an x from both of them. So we take out 3x. We're not going to do anything other than write down what could be factored out here. We only write down what could be factored out. What about down here? 2x and 6. Again, from the last problem, we know that that's going to be 2. We're also going to do the same process with the columns. So, what can be factored out from 3x squared and 2x? It's a little tougher to see, but the only thing they have in common is this one has 2 x's and this one has an x. The only thing they have in common is x. Last but not least, what do 9x and 6 have in common? What can both those be divided by? 9 and 6 can both be divided by 3. So the fourth step is to write out all the factors along the sides and the top. It turns out we actually have our answer now. The fifth step is just to write out the the column here and the row here as 2 different binomials. So we have 3x plus 2 in this column, and we have x plus 3 in this one. That's our answer. And notice how it matches the one we had before, just flipped around. You're allowed to flip around your binomials because they're being multiplied. Just like how 2 times 5 is the same as 5 times 2, x plus 3 times 3x plus 2 is the same as 3x plus 2 times x plus 3. This is the box method, and it might look familiar once you have all the terms written out, because if I put these lines here and a little bit of a multiplication symbol here, it's just our table method for learning how to multiply polynomials. Remember how we had two polynomials on the outsides, and we would multiply them together to get what was in the boxes? It's the same thing, just reversed. Now we have the boxes, and we're factoring out to find the polynomials on the outside. It's just the table method in reverse. That's why the box method is easier, but there's no built-in check here to know if we're doing it correctly or not. So if you're using the box method, you must be very careful to make sure you have pulled out all that you can, and that includes negatives. Here's what I would like you to do now. I would like you to try out problems number 9 and 8. Number 8, I want you to use the box method to solve. Number 9, I want you to use the AC method to solve. Be very, very careful as you go through. Sound good? Pause the video here. Try number 8 using the box method, and try number 9 using the full AC method. We'll come back in a moment. Hopefully you had a chance to try these problems out after pausing the video. We're going to talk through these ones together. Normally I just give you the answers, but that's not going to work here because there's such an art to the process here. I want to make sure we're doing the process correctly. With both methods, we want to set up a combinator, but we don't set up a normal combinator. We set up a combinator where our top is A times C. Remember, both of these processes started the same way, with the combinator of A times C. For number 8, our A is 6, our C is 4, so on top we have 24, and on bottom we have negative 11. So we ask, what multiplies to make 24 and adds to make negative 11? Well, it's got to be two negatives, because two negatives make a positive. The two numbers are negative 8 and negative 3. That's our first step. From here, we now know that this negative 11k is just a negative 8k and a negative 3k in a trench coat. We can split them up into two different terms. So we write out 6k squared minus 8k minus 3k plus 4. We've split our 11 into negative 8 and negative 3. That's the second step. For the box method, we now just put our terms into these nice little boxes. Our 6k squared must go in the first, our 4 must go in the bottom right, but the other two we can flip-flop. So let's put our negative 8k here, and let's put our negative 3k here. Now, this box method was a little bit tricky because we have some negatives introduced. And here's the general rule of thumb. If the term with the higher degree has a negative, pull out a negative. If not, don't worry about it. So here, if we were trying to look at this row, the higher degree term is just positive 6k squared. We wouldn't pull out a negative here, but we would pull out 6 and 8 are both divisible by 2, and both of these have a k, so we pull out a 2k. In the bottom row, 3k and 4, or negative 3k and 4, have nothing in common, nothing at all. But there is a negative here, and it's the higher degree term, so we want to pull out a negative. And what can both 3 and 4 be divided by? If they can't have a greatest common factor, their greatest common factor is 1. So we pull out a negative 1. Again, if the terms that you're trying to factor out from don't have a common term, you can factor out a 1, or in this case a negative 1 because of the negative sign. Let's do the columns. What do 6k squared and negative 3k have in common? Well, both can be divided by 3 and both can be divided by k, so we write 3k. Again, it wouldn't be negative because our 6k squared, our higher degree term, is not negative. But on our last column, the higher degree term is negative. We want to pull out that negative sign at the start. And what can negative 8k and 4 both be divided by? They can both be divided by 4. So the answer to problem number 8 was, I'm going to have to write this down over on this side because I'm running out of room, but 2k minus 1 and 3k minus 4. After you're done with the box method, if you're unsure if you got the right answer or not, the best thing you can do is FOIL to figure out if you get back to where you started. In this case, we would. Let's do number 9, the AC method. So, again, we multiply our A value and our C value, giving us 18. And our middle value is 9. What multiplies to make 18 but adds to make 9? The answers here were 6 and 3. So we write out our polynomial once again, except we split our middle term into 6w and 3w. So we have 9w squared plus 6w plus 3w plus 2. And again, you could have swapped it too, or it was 3w here and a 6w here. Doesn't really matter. The AC method involves us then grouping our first two terms and our last two terms and pulling out what's in common. 9w squared and 6w can both be divided by 3 and w, so we pull out a 3w. And what's left over? Well, 9w squared divided by 3w is just 3w. 6w divided by 3w is 2. So we have 3w plus 2. Here, 3w and 2 don't have a greatest common factor, so what can we pull out? We can pull out a positive 1, a plus 1. And since we didn't really pull anything out other than a 1, 3w divided by 1 is 3w, 2 divided by 1 is 2. And again, how do we know we did this right? If your terms in parentheses match, you did it correctly. So we pull out those terms in parentheses and put them in front. 3w plus 2 goes in front, and whatever's left over goes in its own set of parentheses. We have a 3w here, and we have a 1 here, so 3w plus 1 is our second set of parentheses. That is the AC method and the box method. With that said, everybody, that is the end of our notes for today. Thank you so much for listening, and I will catch you next time.